numbers of particles. Okay, so for hydrogen, so for example, for hydrogen, I have a proton in my nucleus, and we'll talk more about protons and neutrons, and we'll talk more about that in the next unit, as the next unit, and electrons. So the components of an atom, we'll talk more about that in the next unit. So for example, for hydrogen, I have a single proton in my nucleus with an electron. For helium, I would have proton and a neutron in my nucleus with 2 electrons. Okay, so helium has more stuff, so helium is going to weigh more than hydrogen. So the particles that are different between atoms, they're called nucleons. But if you know what a proton and a neutron is, you know what a nucleon is, because nucleons are just protons and neutrons. Okay, so we compare the masses of atoms in something called relative terms. And that means that it's based on a comparison. So let's just take a look at this little diagram. So if I have hydrogen, well, that's my smallest atom. I'm going to say that weighs 1 unit. If I compare oxygen to hydrogen, well, oxygen is 16 times heavier than hydrogen. So oxygen is going to weigh 16 units. So having 1 oxygen is like having 16 hydrogens. For sulfur, it's 32 times heavier than hydrogen. So if I declare that hydrogen weighs 1 unit, well, sulfur is 32 times heavier. So I'm going to say sulfur weighs 32 units. So you get this ratio of masses, and that ratio stays constant regardless of how many atoms you have. So let's say I have 100 atoms of each. So I have 100 hydrogen atoms, that weighs 100 units. I have 100 oxygen atoms, that weighs 1,600 units. So you just multiply your mass by your number of units, 16 times 100. And then I have my sulfur, which is 32 times 100. But if I break down their mass, I still get the same ratio of numbers. Okay, so it doesn't matter how many atoms I have. If I break down the mass, my mass of oxygen is still going to be 16 times heavier than my mass of hydrogen. And my mass of sulfur is going to be 32 times heavier than my mass of hydrogen. Okay, so that's relative. You're creating units based on a comparison. So 1 atom of oxygen is like having 16 atoms of hydrogen. 1 atom of sulfur has a mass twice as heavy as an atom of oxygen. The mass ratio it stays the same.
No,
Even if
16.
we increase the number of
16.
atoms.
1 6. Yeah. 1 6.
So if we had 100 of each atom instead of 1 of each atom, the mass ratio would still be 1:16:32. Okay. Okay, we're going to talk about relative atomic mass a little bit more in the note. It's honestly, it's not something you use a lot. You use something called molar mass more. But IB wants you to know relative atomic mass as well. Okay, so the Avogadro number. Avogadro number is known as a mole, and I remember reading it's called a mole because it's short for molecule. So 1 mole, I don't know why I made this space so big. Oh, I know why. Okay, so I'm going to write sort of a long version of it, but we don't use this version. So 6.022141129 times 10 to the 23. If we were in a class together, like physically together in a class, I usually have a poster of moles, but like no decimal places. I have the whole number on the wall. Okay, so 1 mole is 6.022141129 times 10 to the 23 units. And the units can be anything. A mole is a number, right? So I can have a mole of anything. It's just an enormous number. So if you had something like a mole of marbles, well, those marbles would cover the entire Earth to a kilometer. That's how many would be there. So it's a really big number. But we need a big number because atoms are so small. Okay, so the units can be any sort of entity, like atoms or molecules or ions or electrons, etc. Okay. Okay, so it's the unit of amount in chemistry. Unit of amount is like, we would say, how many moles. Okay, so mole is a fixed number, like a pair equals 2, a dozen equals 12, and a score equals 20. Okay, so that is the amount of units in a mole. So we're going to start doing some calculations, and hopefully you did the factor label worksheet, because really the best way to solve these problems is to use that method. It lets you convert from anything to anything else. However, I'm going to show you different ways to calculate something, but hopefully you'll work up to doing factor label eventually. Okay, I'm going to move this. Is anybody still copying? Not hearing protesting. So remember, this is being recorded. So if you don't get it the first time around, hopefully the video will work out and you can take it down after. Okay. Okay, so we're going to convert between moles and number of particles. Just think to yourself, you've done this before. Like if I have 24 donuts, I have 2 dozen donuts, right? So you're just converting between the counted amount you have of something and how many groups are in that counted amount.
Sure.
So a tablespoon holds 0.500 moles of water. How many significant figures are here?
3.
3, good. 3 significant figures. Okay, so how many molecules of water are present? So we're going to use common sense first. Okay, so I have half a mole of water. Here I have half a mole. So 6.02 times 10 to the 23 is a whole mole. Okay, so I have half of this number. We have half of this number. So whatever half of a mole is, so this is the number of molecules in a whole mole, so whatever half of this is, it'll tell me the number of molecules in half a mole. Okay, so I just divide it by 2. Okay, so let's review a little bit how we're calculating using exponents. Something like this, if this was like a multiple choice question, you wouldn't have a calculator. I don't think you'd have a calculator in your IB exams. You kind of have to do it in your head. But we learned how to do these last week. So 6.02 times 10 to the 23 divided by 2 times 10 to the 0. Okay, so 6.02 divided by 2 equals 3.01. And then 1023 minus 0 equals 1023. So my answer is 3.01 times 10 to the 23 molecules. So if I have an entire mole, I have 6.02 times 10 to the 23 molecules. If I have half a mole, I have half of this number, so I have 3.01 times 10 to the 23 moles. Okay, so I took up kind of a lot of room there, and I'm going to need to, well, let's start on the next question, and then I'll erase. I don't know if you're still writing this or not. Okay, so using factor labels. This is my favorite way to solve questions like this. It's a very versatile way. So with factor label, you have some starting quantity. So I have 0.500 moles. Okay. And now I set up a conversion factor. So what I want to cancel is moles. What I want to finish with is molecules. So 6.02 times 10 to the 23 molecules per 1 mole. Okay. And now my top and my bottom units cancel, and I have 3.01 times 10 to the 23 molecules. Okay, so that's if you're using factor label. You can also use something called the mole bridge. And this is just a diagram that you can memorize. We're going to be using it repeatedly. So it's telling you how to go to different quantities and what you would do with Avogadro's number to do that. So if I have number of moles, so I have 0.500 moles of water. So if I have number of moles and I want to go to number of atoms or molecules, well, I'm going this way. So that means I times by my Avogadro's number. This might be the easiest way for you to do this at this point. Hopefully you can work up to factor label. Okay, so I have my number of moles, 0.500, and I'm timesing it by Avogadro's number, so 6.02 times 10 to the 23.
It starts with 5.
And I put that into my calculator, and I get 3.01 times 10 to the 23 molecules. Okay. Make sure you do the worksheet. IB has some really unique ways of asking you mole questions. It's not your standard conversions. So make sure you do the worksheet. And then ask me questions. And ask me questions if you need help. All right, let's try a harder one. Okay, so these questions can be intimidating. I don't want you to feel intimidated. Just think about it step by step. Okay, think about these questions step by step. So a solution of water and ammonia contains 2.10 times 10 to the 23 molecules of water and 8.00 times 10 to the 20 molecules of NH3. How many moles of hydrogen atoms are present? All right, let's take this step by step. First, we need to find out hydrogen atoms in H2O and NH3. Okay, so let's find out how many hydrogen atoms we have. Let's not worry about moles yet, just about hydrogen atoms. So in my sample of water, I have 2.10 times 10 to the 23 molecules. Okay, so 2.10 times 10 to the 23 molecules of water. Or watch how I set this up. You're going to be doing this a lot. Okay. I don't want molecules of water. I want hydrogen atoms. So for every molecule of water, I have 2 hydrogen atoms. And now I just multiply. My waters cancel. So it's 4.20 times 10 to the 23 hydrogen atoms. Okay, that's how many hydrogen atoms I have. And so now let's do the same thing for ammonia. I have 8.00 times 10 to the 21 molecules of ammonia. So 8.00 times 10 to the 21 NH3 times. So for 1 molecule of ammonia, I have 3 hydrogens. My ammonia cancels. So I have 2.40 times 10 to the 22 hydrogen atoms. Okay, so I figured out how many hydrogen atoms I have. And now I'm going to add them together and figure out my total number of hydrogen atoms. Okay, so I'm going to add these together. So I'm looking on my page and I'm trying to find where I put the answer for this. Okay, so 44.4. So I'm putting this on my calculator times 10 to the 22 hydrogen atoms. Okay, that's how many hydrogen atoms I have.
How did you?
Okay,
How did you?
so this is not proper scientific notation, but let's just leave it like this. This is only an intermediate part of the calculation, so we'll adjust our scientific notation at the end. Okay, so now yes.
Why is it times 10 to the 22 again?
Okay, let's break it down. Okay, so we're going to break down our addition. So I have 4.20 times 10 to the 23 plus 2.40 times 10 to the 22. Remember when we're adding scientific notation, they have to have the same exponent. Okay, so for them to have the same exponent, I need to change one of these.
So you make it 42.0. That's what.
So like if I take my 420, I move my decimal point over. Okay, I'm gonna get 42.0 times
That makes way more sense.
10 to the 22 plus 2.40 times 10 to the 22. And now I can add them. So when I add these, I get 44.4 times 10 to the 22.
I got confused too with that.
Okay, does that make sense?
Yeah.
Okay, good. Okay, so now my next step, so I have this many hydrogen atoms. So how many moles is in this? Let's see how many moles is in this. So 44.4 times 10 to the 22 hydrogen atoms. Okay. I want to get rid of hydrogen atoms. And I want moles instead. So 1 mole is 6.02 times 10 to the 23 hydrogen atoms. So when I do that calculation, I have 0.738 mole of hydrogen atoms.
I'll take.
All right. So
Um,
this is hard. This is a hard question.
Yeah.
I would suggest you maybe do it again on your own, and you see if you get the same value that I got for it. Okay, it gets when we, so I find that with moles, it actually gets easier when you're converting between moles and grams. When you're converting between like number of particles and how many moles, that for me is the harder calculation. So it does, I feel it does get a little easier than this when you're going between moles and grams. Okay. So here, we're going to talk a little bit about, this is a bit of a preview of our next unit, which is all about atomic structure and electrons. So we're going to talk a little bit about it here, just because I need to introduce the concept of a weighted average. Okay, so for isotopes, so in a sample of an element, not all of the atoms will have the same mass. Okay, for example, if I have a sample of hydrogen, well, some of the hydrogens are going to have a mass. So this has 1 proton, so it's going to have a mass, let's say, of 1, right? Some of the hydrogens are going to have a mass of 2. Some of the hydrogens are going to have a mass of 3. So in your sample, if you pick out a random atom, it doesn't mean it'll have the same mass as the next atom you pick out. We call these versions of an atom, we call them isotopes. So atoms of the same element, they'll have the same number of protons, but individual atoms may have different numbers of neutrons. Okay, so such atoms are called isotopes. So the differing numbers of neutrons give the atoms a different mass. Okay, so a sample of an element has a mix of isotopes according to the relative abundance. So abundance just means how many, what percentage of your sample is this particular isotope. And the mass of an individual atom is a weighted average. Okay, so if you had your periodic table, for hydrogen, you'd have this little block, and it would have a symbol, and it would have a number, and then here on the bottom, it would have a mass. So this number on the bottom, that's a mass. But this has a decimal, but that doesn't really make sense. How can, if I'm taking my mass based on like number of protons and neutrons, how come that has a decimal? Shouldn't it be a whole number of protons and neutrons are whole? Well, the way that we get this number on the bottom is we calculate a weighted average. So for hydrogen, okay, 99.99% is this hydrogen with 1 proton. But then I also have some hydrogens that have a proton and a neutron. So this one's a little bit heavier. This 1.01, it comes from a weighted average of your different hydrogens. That's why it has a decimal. Okay, in the periodic table, the mass of hydrogen is 1.01. And that's because it's a weighted average of your different masses. Note there's no units because this is a relative quantity. Okay, so this number is the weighted average of the masses of the hydrogen isotopes. You'll do this calculation where you calculate the weighted average, and then you'll see why this number on the bottom has a decimal. This is super important here, this bottom number. And it'll become interesting because when you do so many calculations with moles and molar mass, you'll start to remember what these bottom numbers are, these masses. Okay, so I am going to go over relative mass. Okay, so the mass of an atom is measured on a relative scale. Okay, that means the mass of an atom is based on comparison. So to do this, to measure the mass of an atom on a relative scale, I need something to compare my atoms to. So that's called the reference point, is what you're comparing your atoms to get a sense of their mass. So the reference point for this scale is the carbon 12 isotope. Okay. It's very common. I was reading somewhere, I think, that the reason why this is used as the standard to measure things against is because it is fairly common element. So carbon 12 is considered the standard. Okay, so we say carbon 12 has 12 units. So if I were to take these 12 units and divide it into 12, so 1/12 of an atom of carbon 12 has a value of exactly 1 unit. And when I'm talking about the relative mass of an isotope, it's measured in these units of carbon. And the mass in the periodic table is the weighted average of these isotopic masses for the element. Okay, so each isotope is measured using these units based on carbon 12. And then when I take the weighted average, I get the mass that's listed in my periodic table. Okay, so I'm going to talk about relative atomic mass, and then I will go to the video, and hopefully you can see the video. Okay, so relative atomic mass, that's the weighted average of one atom of an element relative to 1/12 of an atom of carbon 12. Okay, so this doesn't have units. There's no units because relative, we're measuring this in relative terms. Okay, it means the mass is compared to a standard. So these are average values. Okay, so they're not whole numbers. So relative atomic mass is an average value, so it's not a whole number. So my relative atomic mass, if I take the weighted average of one atom of the element, divided it by 1/12 the mass of one atom of carbon-12.
I need to read over this shit.
Okay, so let's try and watch the video. Hold on, let me try and do this. Okay, let's start presenting. And
What? Yeah. Yeah. Weighted average of one atom.
can you see the screen? I see Hezekiah nodding. He can see the screen. Okay, good. All right, so let's, uh-oh. Shoot. You know what? I have to do some fiddling around. Hold on. Classwork. Why won't you let me click on classwork? Classwork, mole concept.
Oh, brother. Oh, brother. Oh, brother. Oh, brother. Oh.
Just you have the tab open already.
Do I? Oh my gosh. Thank you. Actually, let's go to this one. There's no commercial. Can you hear it?
No.
No.
No,
Is it playing?
it's playing, but we can't
Or you
hear
can
it.
turn up. You have to turn up the volume in the video. And
Yeah.
you see that little icon next to the fast. Yeah.
This one?
Yeah. Just slide it all the way to the right. Then maybe try to turn up the volume on your computer too.
Okay, I can't make it that loud. I'm gonna interrupt the class next door. How about now? Can you hear it?
Nope.
No, it's
No,
not.
that's. I don't think the Google Meets captures the sound.
You can stream on Twitch.
Okay, that's that's a little too advanced for me. You know what? Why don't you just watch the video on your own then? Like you can click it in. Oh, that sucks because now I can't play videos for my grade 12s either, and I had this demo I wanted them to see.
Just
That's
turn on
okay.
the captions.
Just turn on what?
The captions.
The captions? How do
Yeah.
I turn on? Here? Annotations,
Oh, that's tough. There's none.
Oh,
mini player, oops. Okay, that's okay. I'm gonna have to read up on how to play videos in Google. That's all right.
That's cool.
But again, you have it in your notes, so it doesn't mean you can't watch it. You can still watch it. Okay, so this part, when we're talking about moles, the whole part of converting to number of particles or going from number of particles to moles and the relative atomic mass stuff, it's actually, I know it's kind of a complicated idea, but it's actually a really small part of the study of stoichiometry. So what we're going to do when we're converting sort of from moles to grams, that's the big part of this that is actually a little bit easier to understand. Okay, so relative formula mass. So relative means by comparison, right? I always think relative is by comparison. So this is the sum of the weighted average of the masses of the atoms. Oh gosh, this is horrible. Horrible, long definition. I'll write it in and then I'll explain it. Formula unit relative to, these are all IB terms. If I had to teach this my way, I wouldn't really teach it like this, but I do want you to know sort of the IB descriptions for this. Okay, so let's say I don't have an atom, I have a formula. So let's say I have water. Okay, so this, actually that's a bad example. They're talking about formulas. So let's say I have a formula unit of salt. So this is a formula unit. Okay, formula unit NaCl. So if I were to take the weighted average of the masses of the formula unit and compare it to 1/12 of a carbon atom, that would be the relative formula mass. So it's also a relative term without units. Go into your homework and see, they might ask you for definitions of relative atomic mass and relative formula mass, but the thing that we're going to be using the most is this idea of molar mass, okay, which is coming up. Okay, so let's just do some really quick calculations. Okay, so we're going to use periodic table. If you have that out, excellent. If not, that's okay. Just know where I'm coming up with these values. So I want to find MR. So it's my relative formula mass. So what you have to remember with this is that there's no units. So if IB asks you to calculate the MR of something, you would calculate it, but don't put units. If you're calculating molar mass, then you have to put units. Usually when I teach this topic, I'll start with molar mass and then I'll go back into this, but I'm just trying to stay consistent to the IB. Okay, so I have 2 chlorines. Okay, so I have 2 chlorines. Well, the mass of 1 chlorine is 35.45. But I have 2 of them, so I just multiply it by 2. Equals 70.90. So you can explain it to yourself this way. If you had an atom of carbon, it would be 12 units. If you have a molecule of Cl2, it's 70.90 units. So it's heavier than an atom of carbon. But to get a sense of if it's heavy or not, you would compare it to the mass of an atom of carbon. Okay, for this one, we're going to calculate this, but it's easier for us, so NH4NO3. So we're going to calculate this one, but it's easier if we like rewrite it. So N2H4O3. So I'm going to calculate the relative mass for this, okay? So for nitrogen, I have 2 and then times, well, what's the mass of nitrogen in the periodic table? When I go to the periodic table, the mass of nitrogen is 14.01, okay? So this represents my N2 plus 4, okay? And when I look up the mass of hydrogen, it's 1.01. So this represents H4. And then for oxygen, it's 3. And I look up the mass of oxygen, 16.00. So 3 times 16.00 represents O3. And then I plug that into my calculator. All together, hit equals, and I get 80.06.
Round too.
Okay? 80.06. So that is the relative mass of NH4 and O3. Okay, it's 9:31. Let's take our break.
Bro, this is the finesse, man.
And
Record it. You just sleep.
so
Come
let's
to
take our
class,
break, and
you
then
go to
when we
sleep,
come back, so let's do one more calculation. So these calculations, if you know where to look up that value for your mass in the periodic table, the calculation isn't so bad. So when there's polyatomics like this, and I'm being asked to calculate the mass, I would just take out that polyatomic. So this would be Al2S3O12, okay? So I want to calculate the mass here. I'm being asked for MR, so that means no units. Okay, so I have my periodic table in front of me. There's 2 aluminum, and then the mass of aluminum is 26.98. Okay, so this is my Al2 plus 3. My mass of sulfur, let's take my periodic table here. My mass of sulfur is 32.07. So this is my S3. And then my oxygen is 16.00. Oxygen, I think, is one of the ones you'll remember because you use it so often. And I put that into my calculator. I hit equals, and I get 342.17. This is this is a question from the textbook. I don't think this is the right number of significant figures, but that's what they gave in the textbook. Okay. So let's talk about the sort of the big idea here, and that's the idea for molar mass. Okay, that's the idea that I really want you to understand because you use this a lot. Okay, so molar mass, and I am going to scroll way down. Okay, way down, and just talk about molar mass in the blank space here. So molar mass. Okay, molar mass. How much does 1 mole of a compound weigh? Okay. Okay, so I have this quantity, it's a mole.
Yep.
And I want to know how much 1 mole of my compound weighs.
Yeah.
So let's say I have, in my periodic table, I have sulfur.
Me too.
Okay, I have sulfur in my periodic table. This number at the bottom here, that bottom number, that number tells how much
You already know this, right? Though.
1 mole of that element weighs. So if I was to go and if I was to weigh out 32.07 grams of sulfur, I would have 1 mole of sulfur. So 32.07 grams of sulfur is equal to 1 mole of sulfur. Okay. Another way of saying that is 32.07 grams of sulfur is equal to 6.02 times 10 to the 23 sulfur atoms, because that's 1 mole. So that bottom number tells you what you need to weigh out to get 1 mole of that compound, okay? And that's why this is such a beautiful thing to bring into the lab, because now if my equation is telling me that I need 1 mole of sulfur, well, I know how much to weigh out to get that amount. Okay, it all comes from that bottom number in the periodic table. So that's what we're going to do some calculations with. But the mass calculations, you get a lot of opportunity to practice them. Okay. So molar mass, capital M. So I have these other letters too. I have little n. Okay, little n is my number of moles. And little m, let's pick a different color. Little m is my mass in grams. Okay, so if I have my relative atomic mass or my relative formula mass and I express it in grams, that gives me my molar mass. And the units for molar mass are grams per mole. Okay, another way of writing that is gram mole minus 1. And the Avogadro number is defined as that mass of 1 mole, so that the mass of 1 mole of a substance is exactly equal to the relative atomic mass. Okay. So if you want, so again, this is IB definitions. The way that I see this is that 1 mole of something
I don't really understand this.
is that bottom number in the periodic table. That's how much 1 mole of something would weigh. So for your IB definition of a mole, it's the mass of a substance that contains as many particles as there are atoms in 12 grams of carbon 12. Okay. Okay. So we're going to do some calculations. Did I put your mole bridge here somewhere? No, I didn't. I don't know why I took that out. Okay. Okay, I'm just going to do like a little drawing up here. So you have this mole bridge, right? You have it. So we're going to be using this thing. Okay, it's called the mole bridge. So number of moles, mass. So if I'm going from my number of moles and I want to figure out mass, I multiply it by molar mass. If I want to go from mass to number of moles, I divide by molar mass.
So you times if you go one way and you multiply.
Okay, so let's do
Okay, mole.
some calculations. Okay, I have 6.50 moles of NaCl. Okay, so let's say that in an experiment, based on my equation, I want 6.50 moles of NaCl. Well, I can't weigh out moles in the lab, so I need to convert that to grams. Okay, I need to convert that to grams. So the first thing you need to do is find your molar mass. Okay, molar mass of NaCl. So just like we were doing, we're looking up numbers in the periodic table. So NaCl is 1 times 22.99 plus 1 for chlorine times 35.45. Okay, so this term represents sodium, this term represents chlorine. So the molar mass of NaCl, okay, we could write it like this, MnACl equals 58.44 grams per mole. Okay. So let's go from here, and we have 6.50 moles, and figure out how much we need to weigh out to have 6.50 moles of NaCl. So 6.50 moles NaCl, okay? I'm going to set up my proportion, so times. I want to cancel out moles, so that goes on the bottom. I want to finish up with grams, so that goes on the top. 58.44 grams per 1 mole. So I'm multiplying, or you can use your mole bridge. So if I'm going from the number of moles to mass, I times by molar mass. So I'm just timesing by molar mass. So that's equal to 379.86 grams. But based on my significant figures, I need to have 3 sig figs, so that's 380 grams. Okay, so you can write little m because it's mass, NaCl.
Dude, Tan, why did she put the 1 on the bottom?
380 grams. And typically with questions like this, you don't have to do this, but I would put just
Okay.
that's the significant figures one. Okay.
Okay.
All right, how do we feel
Like,
about that?
what does a mole
Any
represent?
confusion? Anything that you want me to explain again?
Like what? Like you know how that's moles and then the other one's grams. Like what does the mole, like the 1 mole, represent?
Okay. Okay, so 0.10 moles of OH ion. So again, I want to go from moles to mass. So I want to go from moles to mass.
Okay.
So I need to times by molar mass. Maybe if we make this a little darker, it'll be easier to see.
Okay. I think I get it. Thanks.
Molar mass. Okay, so let's figure out the molar mass of OH minus. Now, just because it's got that minus, that doesn't make a difference. You can still calculate the molar mass using the same technique. So my molar mass of OH minus, okay, so I just have 1 oxygen, so 1 times 16.00, so that's my oxygen, plus 1 times 1.01, so that's my hydrogen, and that's equal to 17.01 grams per mole. So if I wanted to weigh out 17.01, so if I wanted to weigh out 1 mole of OH minus, I'd weigh out 17.01 grams. So I have 0.10 moles, okay, times. I want to get rid of moles. I want to keep grams. So 17.01 grams per 1 mole. Equals 1.701.
Yeah, it's the same thing.
Again, you're just taking your number of moles and you're timesing it by molar mass to get your mass. So my significant figures would be 1.7 grams. Okay, so here we have,
1 second.
so these 2 examples, these were going from moles to mass. Okay, so we were going from moles to mass. So for the next 2 examples, we're going to be doing the opposite. We're going from mass to moles. Okay, and if you need me to slow down, explain anything again, just go ahead and stop me, and I'm happy to go over what you don't understand. Okay, so here now, we're going from mass to moles. And if we redraw our mole bridge, so I have my number of moles, I have my mass. Okay, if I have mass and I want moles, I divide by molar mass. If I have moles and I want mass, I times by molar mass. Okay, so I have 32.50 grams of ammonium sulfate. I would like to know how many moles this is. So let's take a look at my formula here. So it's easier to calculate my molar mass if I take off these brackets. So N2H8SO4. Okay, so let's calculate the molar mass. So for my nitrogen, 2 times 14.00. So this is my N2 plus for my oxygen, 8 times 1.01. So this is my H8. For my sulfur, I have 1 times 32.07. So that's my sulfur. And then for oxygen, I have 4 times 16.00. So that's my oxygen, my O4. Okay, add those together. And I get 132.17 grams per mole. So I'm going to set this up factor label. You can use the mole bridge though if you want. Okay, so I have my starting quantity 32.50 grams times. I want to get rid of grams. I want to finish with moles. So 1 mole is 132.17 grams. My grams cancel, and I'm dividing by molar mass. So it matches what the mole bridge tells me to do. If I'm going from mass to moles, I divide by molar mass, and my answer is 0.245895.
Never
But to
learned.
adjust it to the right number of significant figures, 10H. Oh dear.
It's 3, right?
Where was I? NH42 SO4 equals 0.2459 moles.
Why did you count that?
Oh, and that's an N. That's a little N. That's not an M. Little
No, that's only for this one has a decimal. That's why.
Okay. Let's do another one. So I have 273.45 grams of dinitrogen pentoxide. Let's see how many moles this is. So I'm going from mass to moles. I need to divide by molar mass. So let's calculate the molar mass of this. Okay, so I'm going to calculate the molar mass
She better
of
record.
N2O4, N2O5.
You need her to record
This
this.
is maybe an easier example than the one before. So 2 times 14.00 plus 5 times 16.00. The number in the brackets are coming from my periodic table. This first part represents N2. The second part represents O5. So my molar mass is 108.02 grams per mole. Okay, so I want to turn this into moles. So let's write our starting quantity. So 273.45 grams times, I want to get rid of grams, so grams goes on the bottom. My moles goes on top. So So 1 mole is
But
equal
I
to
don't get it.
108.02 grams.
Oh, my bad.
Okay, so I'm dividing my mass by my molar mass to get my number of moles.
No, I
And
get
I
what
end
she
up
does,
getting
right? I get what she does,
2.5.
but I don't understand it fully.
Just checking my sig figs. That's 5 sig figs. 1, 2, 3, 4, 5. Okay, so therefore my number of moles of N2O5
But how many?
equals 2.5315 moles.
Yeah, perhaps it doesn't matter.
Okay, that is your introduction to moles.
Miss,
So,
how'd you
yes.
get 0.2 at the end of 108 when the other two are whole numbers?
I don't know. You're right. They are whole numbers. I don't know how I got. Oh, I know why. Sorry.
Isn't it 14.01?
No, 14.01. Thank you.
Bruh.
Miss, could you slow down? I didn't copy the example.
Which example?
The one where you wrote molar mass, like how much does 1 mole?
Here on the bottom?
Yeah, that one.
Okay. Okay, so what we're going to do next is we're going to do something called an empirical formula. Okay, I think there's moles are involved in it, and the thing about condensed school is that
My teacher taught us so different.
typically I teach this lesson, I teach the mole concept lesson,
Such a
and then
weird.
I give you some time to let it settle and for you to practice the concepts. But because we're condensed, I sort of have to move on to the next topic and get through as much as possible. We're already behind, right? Because we started late. So I don't know, I don't know if I'll get through all the material, but in IB, it's really important that I get through all the material because you have that exam at the end of grade 12. So I know it's going by quickly, but there's nothing I can really do about that. So we're going to go to our next topic, and that is empirical and molecular formula. So I'm going to at least start it because we have until 10:20. So maybe we can do the first page of that. And the concept behind empirical formula is fairly simple. The calculations have multiple steps, but hopefully, oh, this is a long one. This is